So it's 5:05. Vanessa, can I start the event?
Yes, sure.
Okay. Good evening, everyone. We welcome you all to the IIB 6-month lecture series on steel bridges presented by along with JSW. Today's session is RK Goel, design of open web girder stressing. I would request everybody to be on mute. To begin this session, I would request Madam Ruhi to make a small introduction on IIB. Please. Thank you, Ruhi. Next, I would request Madam Purnima to please play an introduction video about JSW.
India, a nation powered by 1 billion dreams. Dreams that we aspire to fulfill every day. Together with our collaboration and commitment, as India embraces to be a $5 trillion economy by 2025, we are all geared up to be a part of this monumental journey to usher in a brighter, better future. Together, we touch ordinary lives and make that difference. We better every day. Together, we make steel that you carve into your agri-equipment. Together, we sow the seeds of success. We make steel that gives the grit and grind to your heavy equipment. Together, we change the landscape of our country. We make steel that you beautifully mold into your automobiles, just to drive our nation on its path towards prosperity. We make steel that you transform into solar energy. Together, we steer our nation towards a greener tomorrow. We make steel that relays your transmission lines, just to brighten the future of millions. We make steel that styles your appliances. Together, we bring happy smiles. We make steel that adorns your development projects. Together, we provide shelter to millions. We touch lives, make them better together, every day. We empower communities, make them better together, every day. We nurture dreams, make them better together, every day. As India embarks on its accelerated growth journey, we are firmly placed to leave our mark in it. Together, we touch millions of lives and make them better every day.
Thank you, Purnima. Today's event
India,
is moderated by Engineer Vinay Gupta. Sir, now I would officially hand over the session to you. Thank you. Sir, you are on mute.
Yeah.
Thank you.
Good evening, everybody. I hope I'm audible now. So we'll certainly have a very good session today. I'm quite hopeful. But before that, I would like to share a sad news today, which is about the demise of a very, very important person, very learned person, very hardworking person, Shri S.D. Limay, who was also the chairman of Pune Center of IIBE. So before we observe a 1 minute silence, I will first read out a bit about him so that you're more acquainted with who we are talking about. His full name is Engineer Shashikant D. Limay. He graduated in civil engineering from College of Engineering Pune in 1971, standing first in the University of Pune, and was a recipient of University Gold Medal. He did his MTech in structures from IIT Mumbai in 1973. He joined the Indian Railway Services of Engineering IRSE in December 1973 and held various positions in the engineering departments of Western Railway from 1975 to 1983. He worked as professor in Indian Railways Institute of Civil Engineers, Pune during 1983 to 1989, as Deputy National Projects Director in UNDP projects of development of bridge faculty at IRICEN, and he received training in US and UK in modern bridge engineering for 1 year. And this was under the fellowship of UNDP. Now, he worked with the Konkan Railway Corporation from 1990 to 1998, almost beginning till the end, the famous Konkan Railway Corporation, as chief engineer. From 2001 to 7, he worked as chief operating officer in Indian arm of Messrs. Owen William Railways UK. And thereafter, from 2007 to 2013, he worked as executive director of Stoop Consultants, Mumbai. Important projects that he dealt with were improvement in geometric design of track in sections between London and Glasgow on British Railways to increase the speed from, imagine, 160 to 280 kilometers per hour, much more than any speed that we have, with modern tilting trains. Design of viaducts and underground stations in DMRC, proof checking of designs of cable stayed bridge at Moolchand and DMRC in Delhi, which is very close to us, in fact, wherever our office is in Delhi. Project management of second Mahanadi railway bridge at Cuttack, planning, then this design of cable stayed bridge, ROB, at Santa Market in Nagpur, and so on. He's a recipient, or he was a recipient of several awards. One of them is S.B. Joshi Award for spreading of engineering knowledge of IEI 1996. Distinguished Alumnus Award of IIT Mumbai in 2000. S.B. Joshi Award for Excellence in Bridge and Structural Engineering. He was Distinguished Alumnus Award of National Academy of Indian Railways in 2015. Distinguished Alumnus Award of COEP 2019. And recently he was member technical expert of an advisory committee and technical advisor of Maha Metro, the one which has headquarter in Nagpur, for Pune Metro Railway project, and member technical expert committee on Metro project MMRDA. He was member of academic council of College of Engineering Pune, COEP, that has been his love always. And ICI honored him with a Lifetime Achievement Award very recently, I think in 2021. So now you realize who we have lost and who we are missing today is a very vitally important person for the civil engineering fraternity. So in respect of this departed soul and paying homage to the person, we would observe a 1 minute silence. Please start. Thank you. Yeah, thank you. So anyway, the life must go on. So we will start with our lecture of today, which is by a very important, a very learned person, I must see in the railways, is engineer R.K. Goel. He is a very pleasant, but equally knowledgeable person. So I don't know why there is an echo. Let me a few words about him. Engineer Ravindra Kumar, an IRSC officer of 1998 batch, and he has long experience of design, construction, and maintenance of railway bridge. He has earlier worked at Bridges as Directorate of RDFC, where he has developed various guidelines of steel girder bridges, bearings, dealt with steel like micro towers. So micro towers I also designed in 1980.
So that is an echo from your end.
Yes, what should I do? I do not know.
Now it's very much clear, sir.
Oh, so I need to present this slide earlier once again.
Yes. Ruhi, please do the needful.
Yeah. So, okay, let me repeat in that case. Engineer Ravindra Kumar Goel is an IRSC officer of Indian Railways 1988 batch. He has a long-going experience of design, fabrication, construction, and maintenance of railway bridges. He has earlier worked at Bridges and Structures as director of RDSO, where he had developed various guidelines for maintenance of steel girder bridges and bearings, and also dealt with the steel structures like microwave towers. So I was just about telling you that I also designed some 100 microwave antenna towers to be erected about 100 meters long. 450 towers, 100-meter tall in 1989. Now, he was the key person to revise the fatigue provision in IRS Steel Bridge Code in association with IIT Roorkee. He holds special diploma in bridge engineering from Messrs. Ramboll, Denmark, on the design aspects of Bogeybill Bridge, which is the first steel open web girder bridge in India, having completely welded joints. Comprehensive guidelines for design, fabrication, inspection, and maintenance of FOBs on central railways have been issued by him, which have been appreciated very well. He is a member of Executive Council of Indian Institution of Bridge Engineers, to which he is associated for the last 20 years. In fact, when you talk of FOBs, they may look like simple structures, but they're extremely important. But they really help you cross the traffic or take your vehicle through comfortably. If the pedestrians were to be there and there were no FOBs, you'll have many problems. So anyway, with these words, I'll request now let me tell you about this topic. Design of open web girders. We have heard a lot, I think. A lot of us have heard. But including pre-stressing is a completely new topic. At least for me, it's a new topic. I have heard, of course, once or twice earlier, but it still it has to go to my head properly. So we'll hear Mr. R.K. Goel. So Mr. Goel, please. Yeah, Ruhi, you have to stop the this sharing, and Goel sir will start sharing.
Thank you, Engineer Mr. Vinay Gupta ji, for a very nice introduction. I would like to straight away share my screen. Kindly allow me to do that. I hope it is visible now.
Yes.
I think it has come up. So the topic has already been introduced by Engineer Vinay Gupta, sir. Now this topic is a very intricate topic. Actually, this subject is a very intricate subject. It involves so many things: conceptual design arrangement, and whosoever is designing a open web girder, he has to understand the difficulties in fabrication, in erection, in maintenance, and about the design of joints. He has to take care of the design life and fatigue consideration, most important. So it's a very involved job. So this topic as a whole needs at least 6 lectures of 1 hour duration to get a complete feel of it. But I have been told to complete it in 40-45 minutes, which I will try to do. And I do not know how much justice I would be able to do. And then added to it, I have been asked to include the pre-stressing part of it also. In fact, camber and pre-stressing is a very different subject. It's a very involved subject. And I remember we have been, I have a lecture on IIB on this subject as a whole for complete 1 hour duration. So briefly, I will be giving the concepts of pre-stressing and how they are different from the camber at the end of the main lecture, that is of design of open web girder. So with this brief, I will just like to start. I am not getting.
You're not able to change the slide?
I'm not able to change my slide. Actually, yeah, so I think it is here, right?
Okay.
So just to introduce further, open web girder bridge is also called a truss bridge. So it is used for spans which are greater in length and which cannot be spanned very economically by a plate girder bridge. Usually in railways, we find that limit is about 24.4 meter, and all spans about 24.4 meter. We go for open web girder bridges, and we have got standard arrangements for that, which we will see in greater detail in the coming slides. So in general, truss bridges are used for span greater than 30 meters. I already said economical as full utilization of sectional area of member is made. This is a very important concept to be understood. Actually, the whole stresses are axial in nature in triangulated girders or open web girders. So you make full utilization of the cross-sectional area as compared to, if you say, take the case of plate girders, you have got a triangular type of a distribution of stresses from the compression core to the compression flange to the tension flange. So there you do not get the complete utilization of the cross-sectional area. But of course, there are other advantages. So we go for lower spans, smaller spans, we go for plate girders. And then fabrication, assembly, and launching needs a team of especially trained people. So people go for open web girders when it is really a necessity and a good economy is going to be achieved. So this is the railway practice. In general, truss bridges are used for span greater than 30 meters, and variant type of configuration is used for simplicity. It is a simple triangulation. You can see the sketches below. So I have already said plate girders up to 12.2 meter, 18.3 meter, 24.4 meter are standard spans in RDSO, and span more than 30 meter are 30.5, 45.7, 61.0, 76.2 meter. Now these are the different types of configurations of trusses. People may use it if they are going for non-standard arrangements. So this is a Hove truss, and this is Parker truss having a R shape, and this is the bowstring truss. In fact, this configuration just wanted to show, because nowadays many people are using the bowstring girders, which are again standard designs issued by RDSO. But if you compare that configuration with this configuration, you will find some diagonal members as if they are missing. So I am not very sure whether the stresses are adequately been taken care of, but since these designs are now standardized and people are using it, so I believe the designer, whosoever done it, has taken care of the proper design aspects at the connections. Because in road bridges particularly, the fatigue is not that important, but in railway bridges definitely the fatigue is a very, very important criteria. So such type of configurations, bowstring truss with a triangulated type of arrangement is suitable. But if that bowstring arrangement without diagonal, that is probably a issue that need special considerations in design. So this Allen type of truss, it involves one extra member in the central panel. So all these arrangements I have taken from the net. This is Baltimore type of truss. It is the advantage of this type of truss is that it reduces the panel length. Now coming to the design considerations, there are different forms of open web girder bridges. One is through type of a girder, which is very economical and preferred generally. Then we have got deck type, which can be of underslung type, and it can be of normal deck type, having a rectangular kind of a L section. So up to 30.5 meter, it is suitable because there you don't have a floor system. You have got two leaves of trusses, and over that straight away at the top chord, the sleepers are resting. But if you go for a higher span, then because of the stability consideration, you have to increase the spacing between the trusses, and then you need to design a floor system also. The moment you go for a floor system, the weight of the truss increases, and then the economy is basically not there. So in such cases, people prefer to go again for open web girder. And that is precisely the reason why you don't get a standard design of RDSO for more than 30.5 meter of span. Now, some non-standard arrangements can be designed with semi-through type, where there are issues of vertical clearances, because in open web girders, otherwise, we have got a closed type of arrangement and the top lateral bracings, and the vertical clearances are an issue. So this is a typical arrangement of different members. You can see in the floor members, these are the stringers, and we have got cross beams. Then we have got bracings, cross bracings. So, and then of course in the stringers also we have got diaphragms and cross bracings. This is underslung type of a arrangement. Where the bearings are here, you can see, and the whole span is just like a fish belly. It is hanging down from the bearing downwards. Here there are two leaves over which the straight away the channel sleeper or the bridge timber rests. So components of through girder bridges are floor system. Here we have got cross girders and rail bearers. Then other primary members are bottom chord members, which are mostly tension members, and top chord members, which are compression in nature, which are having compression, and rakers. They can have compression and some bending also because of the wind effects. And then diagonals, we have reversible stress members depending upon what type of configuration we are using. In present Warren type of truss, we are having reversal in the diagonal members, and verticals, they are mostly tension members, and they are also called redundant members because there is very less stress in these members. Now the secondary members are bottom lateral bracings, top lateral bracings, sway bracings and knee bracings, and portal bracings and knee portal. So different kinds of forces are carried by these secondary members also. Then main gussets and bearings. This is a figure which shows different members of open web girder. Here, this is the end floor member. This is intermediate beams. These are the stringers over which the rail passes, train passes, and here these are the bottom chords. This is the end portal. This is complete end portal. Then you have got top chords, and then these are the diagonals. Now, design of bridges of Indian Railways. Basically, we have got standard spans for uniformity and mass adoption. That is the biggest advantage. Then design of standard span, they are all done by RDSO. Approximately 80% spans are standard spans, and 30.5 meter span is very commonly used span. And design of non-standard spans and substructure or foundation, they are done by zonal railways. And there is a concept of equivalent uniformly distributed load, which is a very old concept, and it is being used. It gives you a very good idea about the type of forces that are likely to come in a particular member, and then the superimposition of loads, their effects can also be done by using this approach. So bridge rule contains EUDLs for various types of loadings. They give their EUDLs are for bending moment, EUDLs are for shear force, and besides that, there are longitudinal forces given for different spans in tabular form. So EUDL is the load which induces equal bending moment or shear force corresponding to the worst combination of moving axle loads of rolling stock. So type of truss, I have mentioned Warren truss with vertical for standard railway spans, and other forms can also be adopted as per the site conditions or the situations required. Number of panels, there are norms for that. Weight of the truss versus floor system, the issue is if you have less number of panels, your cross beams would be lesser, but your design of stringers and bottom chords will be increased, will be heavier. So you have to strike a balance, and usually the optimum number is 6 to 10. Then length of panel, it again there is a tug of war between the weight of the truss and the floor system. The optimum length is 6 meter to 9 meter. Then inclination of the diagonals. So the guidelines are you have to keep the inclination of the diagonals from 45 degree to 60 degree. All these things are based on practice, and they have been specified in Steel Bridge Code of issued by RDSO. The height of truss. Now, height of truss through type versus deck type, it is between 1/8 and 1/5 to 1/8 of the span length. And then spacing of trusses, it has to be sufficient to prevent overturning due to lateral loads. Usually, it is more than 1/3 of the height of the truss, and 1/20th of the span. That means if you are going for 200 feet span, then 1/20th is 10 feet, about 3 meters will be the spacing of the trusses. Now, estimation of loads. These are the different types of loadings. And for all these loadings, this is starting for BGML loading is the oldest loading, 1926, then RBG loading 1975, MBG loading 1986, 25-ton loading 2008. Then we are now having new loadings, HM loading and DFC loading. DFC loading is basically 32.5-ton axle load. So for all these loadings, the EUDL tables are available in bridge rules. And the loads are dead load. Dead load is basically dead load of the truss. Then we have got superimposed dead loads that includes the weight of the track, sleeper, and any pathway, etc. All those things. Then we have got the dynamic effects for which the formulae have been given in bridge rules. Then longitudinal forces, raking forces, which are because of the sinusoidal motion of the train, and wind pressure effects, and forces and effects due to earthquake. So we consider either of the two, either the wind or the earthquake, whichever is more, that is considered, depending upon the seismic zone. Now, the dead load is very clear. It is assumed before the design based on the experience of earlier designs. Then after design of truss, the actual load of actual dead load is verified. And if there is difference between the two, then the assumed dead load is revised, and the structure is redesigned with the revised dead load. Now, live load, for that, there are clauses, clause 2.3 of bridge rule. It gives you the formula for dynamic augment. and based on that, we work out. And there are tables given in bridge rules to straight away get this depending upon the loaded length. So UDL for bending moment and UDL for shear force. So these are also given, the tables are given in bridge rule, from where we straight away pick up the UDL. Dynamic effects, I have told CDA. The formula for CDA is 0.15 plus 8 divided by 6 plus L, where L is the loaded length of the span. And it is the maximum value can be 1. Now, longitudinal forces is they are given in clause 2.8 of the bridge rule, and value of longitudinal force due to either tractive effort or braking force. The longitudinal force can come either through the tractive effort or due to braking. So sudden braking, the maximum braking force, whatever can occur in a particular loading, that is given in bridge rule. I will be showing you the tables how they are there in the bridge rules. So values depend on loaded length, maximum of the tractive effort, dono में से जो दोनों whatever is more in between the two, tractive effort or braking force, that is adopted. Now raking forces, they are given in 2.9, clause 2.9 of bridge rule, 600 kg per meter, and raking force not to be considered for calculating stresses in chords or phalanges of main girders. Now the wind pressure effects, they are to be taken as per clause 2.11 of the bridge rules. Wind pressure expressed as a equivalent static pressure in windward direction, and on the leeward direction 50% is taken. So the bridge shall not be considered to carry any live load when wind pressure at deck level exceeds 150 kg per meter square. Actually, that kind of a situation will be for a very brief period of time. So at that time, the possibility of having a live load also on the bridge is very, very low. So this exemption has been given. So wind force, simply wind pressure into exposed area. So exposed area is area of moving load and the exposed area of the truss members. So we will be seeing the detailed calculations for that. Now for seismic forces, again, horizontal seismic force and vertical seismic force, they are calculated based on the consideration of seismic zone, importance of a structure and its soil foundation system. And these are the formulae given in old bridge rule. But now I understand there is a new seismic code come up from RDSO. So those provisions are to be used, which are definitely an improvement over these forces. So this is the way to work out the seismic force. I think the detailed analysis is to be done as per the seismic code. So when we are acting in the direction perpendicular to traffic, then 50% of design live load without impact is to be considered. And when we are considering the live load in the direction of the traffic, it is to be ignored. So analysis of forces. So analysis can be done using the suitable computer programs or by hand calculations. Hand calculation is done using the influence line diagram concept, which is very easy to use. So ILD is basically nothing but the response of a unit load moving from one end to another end over a particular member. So these things are again shown in the tables, which are likely to come in the coming slides. So dead load analysis is simple. We work out the dead load based on the assumed dead load, and then per truss it will be half of that. So they are again calculated. Forces in individual members are calculated based on ILD concept. Now, what are the ILDs? If we see a truss of this kind, so the different members will have different types of influence line diagrams. Now, this is the influence diagram for L0, L1. If I go back, what is L0, L1? L0, L1 is the bottom chord. So when a unit load moves, the force in this member will start increasing, and when the unit load will reach at this location, that is this location, then it is the maximum, and then again it will start decreasing, and it will keep on decreasing when the unit load goes away from the truss. Similarly, this is for L2, L3 and L3, L4. This is loaded length, complete span, and this is for L4, L5, and this is for U1, U2, and U2, U3. Of course, they will be having compression. Then this is for U3, U4, and U4, U5, compression again. Then L0, U1, that is the end portal. It will be again having compression. This is the ILD for that. So these are for the diagonal members. In diagonal members, the stress reversal takes place. When the unit load starts from one side, initially there would be tension, and then after certain distance, then the reversal of stress will start. And this is basically in fatigue analysis, these two loads are added. There is a methodology given in steel bridge code. This is again for L2, L3, another diagonal reversal of stresses is there. And this is for the vertical members, L1, U1, L3, U3, L5, U5. Now, live load analysis is very simple to be done. Based on these ILD diagrams, we work out the total area of the ILD, and the live load. Live load is basically that coefficient of dynamic augment. So we have live load intensity for core members, which is half of the UDL, total UDL that is given in tables in bridge rules for that particular kind of a loading. So end raker has compression ILD, loaded length is length of the span. So live load intensity for end raker is UDL shear divided by twice the loaded length. Actually, we have to see which member will get which kind of a force. So end for the bottom chord members and the top chord members, we take the UDL for bending moment, and for end raker we take the UDL for shear. So CDA for end raker is calculated using taking length as span length. Then diagonal members are having both tension and compression. Loaded length for tension and compression is found from ILD diagram again. Live load intensity and CDA for diagonals are calculated on tension and compression, both based on their respective loaded lengths. So force due to live load is ILD area into live load intensity. Force due to dynamic augment is equal to CDA into force due to live load. So this is very simple. So CDA we have worked out 0.15 plus 6 upon 8 plus L. So longitudinal force taken only for the bottom chord members, because when the breaking occurs, sudden breaking will occur, it will be only through the bottom chords. It will go towards the end end beam and cross beam, and from there it will go directly to the bearings, and through that, from bearings it will go to the abutments, pier or abutments. For bottom chord member in end panel, loaded length for longitudinal force is full span, and loaded length reduces by one panel length as we take bottom chords of other panels starting from end to center. So this is to be taken care of. This is the IRS bridge rule, which gives the loaded length, which is equal to effective spans for bending moment. I will show you the tables. These are just say this is for 25-ton loading, which is very common loading. Most of the bridges are being designed for this loading nowadays. You see the table, total load for bending moment for spans. If the span is say 5 meter, 4 meter, 5 meter, the total load for bending moment is given. Then total load for shear force is given, and impact factor is also given. So one need not to do calculations. Straight away from this table, you will get the three things: total load for bending moment, total load for shear force, total load, live load due to impact. This is for longitudinal forces again. The tables are given. Tractive effort, braking force, and maximum longitudinal force, which is maximum of the two. Tractive effort or braking force का जो maximum होगा, that is over here. So it varies as per the length. Now wind load analysis. This is a general concept of load transfer and how the wind forces are distributed among the members. So wind load is basically wind pressure into exposed area. Exposed area is area of moving load plus exposed area of truss member. So if this is the truss and this is shaded portion is the moving train, then we have 5 regions. One is the bottom chord area. Other is the bottom chord to moving load in between the moving load and the bottom chord. That is the area second. Then the moving load area 3. Then over the moving load and below the top chord area 4. Then the top chord, that is the area 5. So these 5 regions are there where the wind is to be seen, how the wind forces are acting. So this is a typical way of working out the wind load. Between rail level and bottom chord, this whole force is worked out based on the area multiplied by the wind intensity, and this is carried by the bottom chord. Similarly, the area between moving load and rail level of stranger, that is the area B2, it is again carried to bottom chord. Then moving load B3, there is a separate way of analyzing the effect of this force. Then top chord and top of moving load T1, top chord T2, and then gussets at the top T2. Again, all these are added. This is again shown in different way. So I think it's very clear. A, B, C, D, and E and F. Now summary of projected area, bottom chord and top chord. We work out how much is the exposed area, and this is the way we work out the wind force. Top chord wind pressure 80 into 1.5. This 1.5 has been taken because on the leeward girder, 50% of the wind load is assumed. This is as per the caudal provision. So wind force on the bottom chord, this is 1.5 into A, B minus B3 plus B3. So a nodal force at the top chord and intermediate nodes, then it is distributed on different nodes. Similarly, in bottom chord, it is distributed on different nodes. And then we do the analysis in a horizontal plane also for the wind analysis. And this ultimately, all this load is taken care of by the bracings, top chord bracings and the bottom chord bracings. They are designed for the analyzed stresses. Now, seismic force analysis. Seismic force is calculated in horizontal and vertical direction. In horizontal direction, seismic force calculated for bottom chord and top chord. And on bottom chord, seismic forces due to dead load as well as live load. On top chord, seismic forces due to dead load only. It is obvious because the bottom chord is carrying the whole weight of the moving train also. So in vertical direction, seismic force is due to dead load as well as live load. And analysis of seismic force for forces in members is same as that of wind force. Now, force in truss member found by adding forces due to dead load, then live load, and then the dynamic effects or the basically live load. Live load is basically due to dynamic effect, and live load and dynamic effect. Yes, that is the dynamic effect means CDA, effect of CDA. Then longitudinal loads, wind loads, or seismic loads. The higher of the two. Now, design of stringer, it is done just like a plate girder. So I will not go into detail of this. This is simpler. Similarly, design again. This is design of stringer only. Design of connection between web and flange. It is done for shear calculation of horizontal shear at the level of weld. That is very important. And permissible stress in weld is taken from the appendix G of SBC and clause 13.4 of welded bridge code. And size of weld is calculated subject to clause 6.2 of welded bridge code. Basically, the point is there are guidelines given for design of each and every component of the open web girder in steel bridge code or relevant other codes like welded bridge code or bridge rules. Now, design of stringer, provision of stiffeners is made. There is relevant clauses there. Design of stringer bracings, calculation of lateral load, how it is to be done, clause is given in bridge rule, and analysis for force in stringer bracings. Again, there are provisions. Design of stringer bracings is done as per 6.2.3 and 3.8 of steel bridge code. Now, design of cross girder is again as per the plate girder design. Simple methodology. Only thing is L for CDA is taken 2.5 times of the cross girder spacing. This is specified in the table where the CDA values are given in bridge rules. Now, again, connection of cross girder with stringer. This is very important. Number of rivets are to be worked out for one span loaded or both span loaded, both the conditions. And connection of cross girder with vertical and bottom chord. Connection of cross girder with vertical and bottom chord. This is very important. Actually, there are typical arrangements of a triangular member being which is designed to ensure that there is no subsequent deformation taking place at that location. Now, design of bottom chord, they are designed as tension members. And section assumed for bottom chord members, that is taking into consideration clause 4.5 and clause 6.7 of steel bridge code. Effective sectional area of section is calculated by deducting the area for the holes that we make for the rivets or the bolts. Nowadays we are having HSFG bolts, so the net area is to be taken into consideration. Actual stress is calculated for axial tension for without longitudinal and seismic or wind forces, and with longitudinal and seismic or wind forces, two types of conditions. This, I think, we will be more clear when we see the table. Design of bottom chord may, again, permissible stress for wind, or if we are designing it for the occasional loads, that is wind or seismic, then the permissible stresses are increased, and section is to be safe in both the cases, with or without occasional loads. Then design of stitching weld, calculation of force at the level of weld. Permissible stress in weld is to be taken by the appendix G of steel bridge code and clause 13.4 of welded bridge code. And then size of weld is calculated based on clause 6.2 welded bridge code. So design of lacing and wetting of tension members is given, provisions are given in clause 6.9 and 6.10 of steel bridge code. And design of diaphragm is as per clause 6.16 of steel bridge code. Now, design of top chord, it is done for the compression. The design is done as per the compression member, assuming the top chord as compression member. And section is designed as per clause 4.5 and clause 6.2 of steel bridge code. Effective area of the section is taken as per clause 6.2.2 of steel bridge code. Again, actual stresses calculated for axial compression without seismic or wind forces and with seismic or wind forces. And permissible stresses in axial compression is minimum of basic permissible stresses, then stress in axial compression and permissible stress in fatigue. So the minimum of the three. Again, this is the same clause, permissible stresses are increased by 16.67%. And this is again design of stitching weld, design of lacing bracing, this we have covered. Design of end raker, it is again subjected to, this is subjected to axial compression and some bending also. This bending comes because of the wind effect or the seismic effect also. So section is assumed for end raker, taking into consideration clause 4.5 and clause 6.2 of steel bridge code. Effective area of section is to be taken as per clause 6.2.2. So again, without seismic or wind force, or with seismic and wind force. Permissible stresses again as per code. So all these things are again a mere repetition. Diagonals, verticals, designs are reversible members. Diagonals are reversible stress members. So they are to be subsequently, after we do the complete design, every member is to be assessed for a specified design life, that is of 100 years, and a specified loading intensity, that is the annual GMT, that is 50 GMT. So that is for the fatigue, to ensure that the 400 years there is no damage in the in any of the member or any of the connection because of the fatigue. I think I can skip this because this is design of top lateral bracings. All these bracings are to be basically designed for the wind forces that are to be taken care of, and all these forces are calculated by analyzing the horizontal truss at the top level and the bottom level also. Design of bottom lateral bracing, similarly, because of the wind forces, the bottom frame in a horizontal plane, it is to be analyzed. Now, coming to the design of joints, connection at intersection is done as per clause 6.12 of steel bridge code. Rivet value is calculated for rivets. Nowadays, HSFG bolts are used, so we can calculate the value of the HSFG bolt, how much one HSFG bolt can contribute to strength. Then number of HSFG bolts are to be calculated based on force in the member, simply by dividing the force by the rivet value or the HSFG bolt value. So the arrangement of rivets at a joint is to be done as per clause 7.1 to 7.9 of steel bridge code. Splicing of members is done as per clause 6.11 of steel bridge code. Now, this is the summary table that we get by doing the analysis. You see there are different members in the first column. Then this is the ordinate of the influence line diagram. If I am not wrong, total length, ILD area. Yes, this is the influence line diagram. Ordinate means maximum height of the influence line diagram in tension or in compression. For bottom chords, you will have only the tension. This is the ordinate, and this is the loaded length. That is the full span length. This is a 78-meter span, and we work out the total area of the ILD. That is it. So that way we get the ILD area for each and every member. And this ILD area comes over here. Then we have got dead load intensity, that is ton per meter, total load of the truss divided by the total length in centimeters. In ton per centimeter, we get this load intensity. And similarly, we have got live load intensity. And then we have got the CDA. So this is the live load, this is the dynamic augment. So these values are obtained. Then next table, we get the values of the forces that are coming in different members, like L0, L1, the total tension, this much is the tension we are getting. Top chords, this much is the compression we are getting. Due to, that is due to dead load, then we get due to live load, tension. Then impact load, again tension. Forces in member without occasional loads. So if we don't consider the earthquake and wind, then the total force in that particular member is tabulated here, right? Similarly, top chord, and then you see the diagonals, you will get tension and compression both. These are the diagonals, you get tension as well as compression. So the complete table we get. Now, similarly, for seismic and wind force के लिए भी table बनती है. Forces in member without occasional load that we have got. Then we work out the forces due to wind and longitudinal force. They are tabulated here because of the seismic force. They are tabulated, and if you see in this particular case, the seismic forces are more. Either this is 344, this is 384. So seismic forces are more. So we ignore this wind forces, and we take into consideration the seismic forces along with the other forces. So this combination will prevail over here. Now, after doing all this exercise, we get the stresses, forces in the individual members. Now, after doing this, we will do a fatigue assessment for the design life of 100 years. For this, the clause 3.6 of Steel Bridge Code under the title fluctuation of stresses gives the provisions, and that complete fatigue analysis is done, for which I think IIB is having a separate lecture on it on its website. One can go through that to get a first-hand idea about the fatigue life assessment. Now, the concept of camber, which is very often misunderstood by the people. Many people consider that we get the pre-stressing in individual truss members because of camber only. Whereas there are two concepts. One is camber and other is pre-stressing. The two are entirely different concepts. So this difference I would like to explain by these 3-4 slides that I am showing you. So camber is a functional requirement to avoid effects of vertical deformation under moving trains. If you make any beam and you load it, you will definitely get some deflection, some deformation. And if you want under service conditions, there should not be any deformations. So you have to provide the upward camber in advance so that when the actual deflection comes, so practically an observer does not see any sag in the beam. So that concept is used in camber basically to neutralize the deformation. Now you can see this shape of the truss. This is the shape of a normal truss, and if we load it, then usually we will get some deflection, which will be maximum deflection under the given design loads. And if we want the deflected shape to remain horizontal, then we have to provide upward camber so that when the load actually comes, this deformed shape is practically in a horizontal plane. So this is for neutralizing the deformation. Now, pre-stressing concept is a different concept. It is done in addition to the camber to develop reverse kind of stresses in various members at the stage of no load. So no saving of material is intended over here. However, we get some economy besides getting reduced stresses during the service. So girders can be designed as cambered with or without pre-stressing. And there is a clear-cut provision given in steel bridge code, which says that you can design the girder as only cambered girder, and it is preferable to design it as cambered plus pre-stressed. So there are some differences in the design provisions for doing that. So the advantage is the secondary stresses are ignored if we are designing the girder as pre-stressed girder along with the cambering. Cambering is essential. So a lot of quality control in fabrication is required when we design the girder as pre-stressed girder. Now to explain the issue further, the shortening and elongation of member, how it is helpful in giving some kind of a pre-stressing in the members. If you see the second picture over here, we have got a fixed length A and B between the two supports, two fixed supports, and we have got a member, steel member of course, which is of length L. And I want to have this member to have some pre-tension or pre-compression. In one case, I want to have pre-tension. In second case, I want to have some pre-compression introduced. So what I do to introduce the tension, what I will do, I will fabricate the member in such a way that the actual length is less than this length AB. So A1, B1 length, if it is less than AB, then there is a shortening of the member length. So my deformation is delta L, and delta L, FL upon AE formula if I apply, then I get that amount of shortening that is required to introduce the tension amounting F1 force. Similarly, for introducing compression, I will have to increase the length of the member originally, and then when I will do force fitting in between A and B, the member 2 will definitely get some compression. So concept is simple. Camber is to neutralize the deformation and pre-stressing is to neutralize the stresses. Now we can say a simple bracket arrangement. If I take in black, if you see, there is a bracket ACB. If I make a bracket ACB and no load is applied, then this member AC will be horizontal and BC will be as it is. And under a load W, this C will come to C dash. There will be some deformation. And this will be the deformed shape. In green color you can see. And if I want that after deformation, this member AC dash should remain horizontal. Then what I will do, I will make this member AC something smaller in length, so that this point C dash is somewhere here, and this member BC again something some longer, so that it comes here. So if we draw a perpendicular from here, so I will get this much of elongation. So when I make this structure in such a way, then after application of load W, this C double dash will come at C, and there would be no deformation seen practically. Now, if I want to introduce pre-stressing also, now A, C, B, I have fabricated in such a way that it is having camber, and after deformation, this C will come here. But at the same time, now I want this member, which is usually supposed to have tension, that it should not have any tension after loading with W. Then I will do some kind of a elastic shortening and elastic elongation. So this, to introduce compression initially, I will have to make this member a bit longer and this member a bit shorter. And by force fitting, I will put both these members at C. So then finally, this member, when loaded with W, it will be theoretically having no stresses, and it will be having no deformation also. Practically, no one will see that there is any deformation, and theoretically, there would not be any stresses in both the members. So this is in nutshell the concept of pre-stressing, which is being practiced in all the designs of RDSO standard trusses, and many people are not aware of it. So this is important to know, because many times we are dealing with the existing open web girder bridges also. So we must know that this is a advantageous situation for the bridges which have been designed with pre-stressing. All these things are, I think, I can leave now. This I have explained already, and this is the amount of deflection that we assume while giving the pre-camber. Thank you very much. I hope I could not breach the time limit given to me. Thank you, sir.
Thank you, Mr. Goyal. Very interesting. And I am hearing this presentation. That is the last part, I must say, probably second or third time. But still, I am trying to scratch my head and understand. Really interesting and very useful, I must say. First of all, before we go into our panel discussion and questions and answers, I must ask Ruhi, are you ready with the can you project the slide for the next event, which is on 27th in May in Delhi?
Yes, sir.
Can you please project that for the people's information? Okay, while you're projecting that, in the meantime, I'll inform all the audience that the next lecture of this series, which will be the fifth such, the series that is sponsored by GSW, and of course, that's a great help that they have provided to IIBE, will be on 17 June. Dr. Harshavardhan Subbarao, he will be the speaker, and he will be speaking on a 4.4 kilometer long Digha Sonpur rail cum road bridge in Bihar, which means more like a double-decker, similar to one you see here in the picture, although that is a different context, and 4.5 kilometer long, which they were involved in. Then the last one, that is on 15 July. So the first one I said is 17 June. Please come one, come all of you must join, and also get others to join. On 15 July, we'll have a presentation by engineer V.N. Hegde, and he'll be presenting on another different topic. Unlike you saw this, other way you saw pre-stressing, you'll see a topic there which is decarbonization of steel. Decarbonization of steel for durability. Then followed by, following that, we will also have a panel discussion, which will be like the end of the series of 6 lectures, ending with a panel discussion with a lot of enrichment of everyone's knowledge, including that of panelists and yours. And now coming to what our head office has projected to you. Can you put it on full screen, Ruhi? Ruhi, okay, it's a PDF, fine. So friends, we have also started organizing in-person physical events. And next event that we have will be on 27th May in Delhi, place called CSOI in Chanakyapuri, which will be basically on double-decker bridges. And there are two presenters of two different projects of double-decker. One is Dr. Professor Anurag Mishra, Professor Dr. Anurag Mishra. He is from IIT Jammu. And the other is Mr. Sai Baba Ankala. He's a part of Indian Railways, very similar to Mr. R.K. Goel. And both of them will be presenting their respective double-decker bridges. Now, double-decker precast segmental, when we are talking about, this means that the lower deck, which is a wide one, carries the highway traffic, the road traffic. The upper one, which is a narrower one, it carries the metro. And the construction and design both, they become a challenge. For one reason, that the pier from the lower deck passes through the lower deck and go to the upper deck. So there's a different design concept. Another challenge is how to erect both these segments, the upper level, lower level, that without hitting the crane, while you're erecting one, the other one should not get hit. Those things will be discussed threadbare. And I know that the project of Professor Anurag Mishra is Jaipur Metro double-decker. In India, so far, we have 3 double-deckers. One is Jaipur, other is Nagpur, third one is coming up in Pune, and fourth one is coming up in Delhi that we are designing, Delhi Metro. So we'll have very interesting presentation. Of course, we will follow it by cocktails and dinner. So please come and join at Delhi. Thank you so much. And Ruhi, thank you for projecting it. I'll go to the next part of it about this, I would say, the presentation. I must say that Engineer Ravindra Goel has presented a real life method of analyzing and designing open web girders. Because the way he explained each and every aspect of designing, of course, we'll have questions from you, and please feel free to ask as many questions as you like. He even went to the grassroots level of ILD, influence line diagram, in bottom chord, top chord, bracings, everything. So that's where we are. And the other thing he told about how to take there's a confusion he clarified among the people's mind, the span L for coefficient of dynamic augmentation. And that span L is between the cross girders and not the whole span. There's no confusion, is very clear. And lastly, of course, he explained very well about the pre-stressing and its purpose. Like we talk of it in concrete, where we pre-stress it to counteract the tensions that we have. So here again, we counteract the pre-stressing, the rather tensions through pre-stressing in steel, apart from cambering, apart from shortening the length, and apart from sort of varying the length, that finally after loading, it should come to the required profile. But then we also providing some kind of a pre-compression kind of a force in the steel. In fact, I would have been very happy if there were some pictures to show how it is done actually. So on the whole, very interesting, very pleasant, and very pioneering kind of a concept. And he said the railways are always using it. I just did not know. Maybe many of you would. So I think with these words, in a way, I'm done. Now let me see who are the other panelists before we go to the questions. And in the meantime, I request all the audience to please put your questions in the question answer box, Q&A box, please. So first of all, our sponsor, Mr. Vinay Pandey, would you like to say something? Because I wanted to actually convey a message to everybody, which I forgot. The message is that we must not be biased towards concrete or steel. As engineers, we must decide, we must make a right choice that in which conditions steel is better, in which conditions concrete is better. both of them have some merits and some demerits and some limitations. For example, if you're worried about a weight somewhere, whatever be the reason, but if there is a weight, then no matter about durability, cost, this and that, because there are ways and means to counter that, you have to go for steel, and you must go for steel. Then there is a thing that you want something to be looking as nice as concrete in some funny shapes, or maybe 3D printed concrete, then of course you have to go for concrete. But usually in both these nowadays, we go for segmental approach. In concrete, we tend to go for precast segmental and pre-stress it. In steel also, we manufacture long beam, truss, whatever, in several segments which can be transported, brought to the site, assembled using HSFG boards, which Mr. Arkegoel said. And these HSFG boards have become increasingly popular for the site fabrication. And the fabrication at the factory, a workshop, would be done normally using submerged arc welding of a bridge quality welding, I must say. So I think we have both the choices, but and I said we should not be biased on anyone. We should not say concrete is superior or steel is superior. We must weigh the merits and demerits of each in the given conditions, and then tailor the product, be in steel or be it in concrete. I request Mr. Pandey to please say a few words.
Thank you, Mr. Gupta. First of all, thank you very much, Mr. Goel. It's a wonderful presentation. And I, on behalf of JSW, I thank all participants. This is a knowledge sharing platform, and the entire series of lectures are part of knowledge dissemination program. Basically to enrich people who has, there are a lot of engineers who has designed wonderful bridges, who can share their case studies to the other audiences, participants, who can learn from there, and moving forward, they can design wonderful bridges for the country. So I thank everyone for participating in this, and thanks Mr. Goel for sharing such knowledge. Now coming to one thing is the steel, definitely a steel, each of the product, as Mr. Gupta explained, has its own advantages, and all the materials should be used to its maximum strength. Steel has got the wonderful quality of circular economy. It provides circular economy. So it is recyclable 100%, and without compromising on any strength, you can recycle it. So today, if you are making a structure in a steel, 100 years down the line, you are creating an asset for the future generation, because the circular economy will also decarbonize the entire construction process. So that's the advantage which the steel brings in, added to the other technical advantages which Mr. Gupta has already explained. So thank you once again to Mr. Gupta, to Mr. Goel, and all participants. I hope they must have enriched their knowledge with the wonderful design concept presented by Mr. Goel, especially camber and pre-stressing. Thank you very much.
Thank you, Mr. Pandey. May I now request Engineer Tarun Goel, who I have been closely associated with, very knowledgeable person. And when we think of steel, we think of Tarun Goel, or when we think of Tarun Goel, we think of steel.
Thank you for your kind words. Thank you for your kind words. So it was a fantastic presentation, and Mr. Goel touched upon various aspects of open web girders in great detail. And I'm sure every participant must have found it interesting and learned from it. I mean, design of steel bridges, particularly open web girder, is a vast topic. However, it was covered efficiently in the presentation. This topic does not, not only requires deep structural knowledge, but also field knowledge, because how we are executing a bridge, what kind of connections are being used, steel, is it HSFG bolts, or is it welded type? So that thing needs to be catered into the design. So that's how it is a little different from pre-stressing or pre-stress bridge or concrete bridge. Would also request Mr. Goel to touch upon assessment of fatigue design life of existing old bridges, maybe in another another presentation, because there in Indian Railways there are many old bridges which have passed their lives. So we need to assess from fatigue criteria whether how much life is remaining for those bridges. So we'll request Mr. Goel to take upon that topic in another presentation. And I once again thank Mr. Goel for that delightful presentation. Thank you.
Thank you, Mr. Tarun. So, if everybody permits, I'll take up the questions. We have about 15 to 20 questions in the question box. The first question is by Ashish. Why is it that EUDL up to 10 meter for maximum bending moment, and after 10 meter, it is moment at 1/6 of the length? So, can you answer?
Actually, I have shown you a sample type of a page. Actually, the complete table goes into 2-3 pages. I have, for the purpose of making the slide, I have used only the first page. So if you see the bridge rule, you will get more pages. You will get the more spans also.
Right. So the next one is by Thota Murlidhar. Wind load is to be considered both on the train as well as the truss also. Is it okay?
That is right. Actually, wind is to be considered for 5 different regions, which I've explained. One is the bottom chord, and the second is between the bottom chord and the moving load. Third is the moving load. Fourth is the moving load, and below the top chord. Then the fifth one is the top chord. So for all these components, there is a definite set of procedure which is to be adopted for wind load analysis.
Right. Ms. Harinder Dogra is asking, very interesting question. Does the speed of train affect design considerations?
Yes. Actually, the this is part of the bridge rule. When we talk about the speed, it is basically a load. It is part of the load. If you increase the speed, your dead load remains the same, live load remains the same, but the impact is increased. So the CDA formula that we have in our bridge rule, that caters for a speed of 165 kmph for passenger trains and 125 kmph for goods trains. So up to that speed, if you are running the trains, then there is no need to worry. They are taken care of by the CDA. But if you have to design a bridge for a speed in excess of 165 kmph, then you have to account for, or you have to suggest some modification in the CDA.
So a question may come that if the speed is only supposing less, say about 80 km/h for whatever reason, can the CDA be reduced as well?
The question is whether you are designing for the Indian Railways or you're designing for some private railway. If for some private railway, then you can definitely reduce. But if you are designing for Indian Railways, and that too for a standard span, then you have to adopt for the codal provision.
So his next line on the same question was, increasingly higher speed are being achieved. So what is the impact of this?
Up to 165 kmph, I have told there is no issue. If you are going higher than that, and if it is a passenger train, then you have to work out what is the effect on CDA.
So nowadays we are dealing with a lot of high-speed trains like 300 km/h, 225 km/h.
Yes, you will have to increase the CDA.
So in that case, we need to do dynamic analysis, like for NCRTC.
That may be required, may not be required. Actually, the problem is there is a very limited research in this field in the country.
Right.
Whatever research is there, that is there in other European countries.
Right. So next one is Venkateshwara Rao Surati. What kind of protection is envisaged for a steel truss bridge against corrosion? Let's say design life of 100 years.
Actually, this is a very important topic and it can be covered in a 1 hour duration. If you ask me, there are different kinds of systems. One is a normal conventional system wherein we do the painting. We do the first primer coat, then a intermediate coat, then the final coat. There is a complete scheme of painting given in B1 document that many of us know. and that is to be followed. But if somebody is interested to have a higher type of a production, there are long life painting schemes available. So up to 15-20 years, they don't require any second attention.
Which means paint will not have a life of 100 years. You have to go on redoing it after 15 years or 20 years or whatever.
Okay, it's a very interesting question, actually very close to my heart. The real production to steel is the primer coat, which many people they forget to apply. They straight away apply the finishing coat. So we have to understand the complete philosophy. How does it work? It's a complete system. You have got the primer coat which protects the steel. Then you have got a intermediate coat many times, or you straight away have two coats of finishing paint. So the finishing paint, the finishing coat, that protects the primer. So with this 3 tier of protection, there is no other protection required. If you keep on after every 5 years, if you keep on doing the finishing coat once more, then your primer will remain always intact. And the second problem is that when the people inspect the bridge, they see the main member, they don't see the connections. And these connections are the critical areas. And these are the locations which are very difficult to inspect. These are the locations which are very difficult to paint. So one has to focus on connections if you want to increase the design life of the bridge, rather the not the design life, the service life of the bridge.
Yes, thank you. Another one from Harinder Dogra is, sorry, IS 800 is a steel code. Are you using this code or not?
IS 800 is basically for buildings.
Is SBC same as IS 800?
No, steel bridge code is an entirely different code. It is dedicated to steel bridges of Indian Railways, and it is to be used in association with bridge rules and IRS steel welded bridge code and other guidelines for fabrication and inspection.
Well, that's Indian problem. We have IRC for highway bridges, we have BIS for buildings, we have IRS for railway bridges, and God knows how many. But we can't help it. We have to follow within their domain.
Yes.
Deepak Shinde has a question. How the ILD ordinate is greater than 1 in summary table?
I don't think it is ILD ordinate. It must be the total area of the ILD diagram.
Okay. Our very young civil engineer, Dr. S.K. Dhawan, I think nobody can say he doesn't know him. I think he's around 75, 80 years old, recently done his PhD. He has some question. Question is, please explain the adequacy of section in the design of open web girder bridge.
Yes. So there are 3 types of members. One is the tension member, other is the compression member, and the other is the bending member. So in bending members are basically the cross beams and the stringers. They are bending members. And you have got the bottom chords, tension members, top chords, compression members. So the tension member is to be designed based on the net area concept. At the connection, when you detect the area for holes, then whatever net area you get and the permissible stress, so you work out how much is the net area requirement. That is very simple.
Okay. So the next one is by Muhammad Yunus Ahmed. How to apply pre-stressing in open web?
Actually, I would request you please go through the IIB website. There is a complete lecture on it. You will find it very interesting, and you will get all the answers there.
But can you give a gist of it so that at least
I have explained in the last slides. See, what is pre-stressing? You have to introduce a reverse kind of stress in a particular member. Suppose you are having a tension member and you want to have no stress during finally under the load. So you would like to pre-compress it. So for doing the pre-compressing, for introducing pre-compression, you have to increase the length of this member in between the two supports and then do force fitting. When you will be doing force fitting, you will be compressing this member to the actual length that is required in between support A and B. And when you fit it and leave it, then this member will be having the compression. So when the actual tensile load will come, so this will get negated.
Right. Naveen Kumar Chaudhary is asking, can you share this presentation to attendees?
I think some recording must be done. I think, are you doing some kind of a recording of this lecture that can be shared, I think, in IIB website?
Recording is being done, but basically recording is not as such supplied in terms of what do you call it, pen drive or something or website. But since live streaming is being done, it will be available on YouTube. Am I right, Rohi? Rohi, can you unmute and tell me? It will be available on YouTube, I guess. Oh, sorry. She is probably not there. Okay, we'll answer this question in a while.
So the video is right now live streamed on YouTube. So they can just go to our channel at IIB and they can see the video.
And will it be available later also?
Yes, sir.
Okay. So I think that answers the question. Hemant says, thank you, sir. The talk provided strong foundation for open web girder bridges covering influence line diagram, loading element of bridge, IRS clause, and deflection. So he is praising
Thank you for your
detailed presentation, as I also said. Okay, so Kalyan Sarkar says, sir, thank you very much for the presentation in such a lucid and simplified manner. Do we do fatigue check for diagonal members only or for all members?
Yeah, this is done for all the members and all the connections. This is a very involved job, and there is a separate lecture on IIB website for this.
Right. Pritesh G. Thange, his question is, why is it said that pre-stressing is not considered as a method to economize the design in steel?
The codal provision of IRS Steel Bridge Code says that you will design the open web girder as a pre-stress girder, but you will not take the advantage of pre-stressing. So basically, you are giving this as a extra safeguard.
Yes.
You understand? Am I clear about it?
Yeah. It does not go in costing, but it goes in quality.
It will basically improve your life.
Right.
The bridge will not get stressed to the actual stresses. And in fact, when you do the instrumentation, this is very important to note. When you do the instrumentation, you will find very less stresses coming at the locations where you can intend the stresses should be more. So that is because of the pre-stressing. So when you know this thing that all open web girders designed by RDSO are being designed as pre-stress girders, so you will know why the stresses are coming low.
Safi Halim has a question. Cambering is done for live loads also. That's a question he's asking.
Cambering is done for live load. If you are designing it as a pre-stressed girder, then the cambering is done for the dead load plus full live load and full impact load. Live load plus impact load plus dead load, full, complete. But if you are designing it as only cambered without pre-stressing, then the live load is taken as 75%. This is again given in relevant clause in IRS Steel Bridge Code.
Okay. Another encouraging question from SIR, I don't know what its full name is. The organizer is required to arrange a webinar on Flexi Arch Bridge. So let us see if we get some good speakers, we can arrange a set of lectures on Flexi Arch bridges. Another question from the same person. What are the root causes or root cause findings of few major incidents happened in the station platform FOB and recommendations to avoid similar incidents in future?
And one of the main cause is lack of awareness about the design practices and the lack of interest in learning the subject of bridge engineering. And added to it, there is no separate branch of bridge engineering in India. Rather, we have tried to see it as well also. There is very few places where we have a separate branch of bridge engineering. So we have to encourage this. We have to say it often that we need a separate specialization for bridge engineering so that our people are more aware they can take more confident decisions. There are less confusions, and they are more confident.
So Hemant's next question is it only primary member connection are using HSFG? Can secondary member connection the primary and primary with grade 8.8 or 5.6 bolts without DTI washers?
This is a very practical question, and I had a real problem about this when I was in charge of the workshop at Manmad. Actually, the design provides for HSFG connections even for the secondary members, but the guidelines which have been issued for HSFG bolts, that says that the surfaces are to be, first of all, they are to be sandblasted, then only HSFG bolt is to be provided. Now, practically, it is not possible to carry a member to the sandblasting section, and then just for the sake of providing HSFG bolt for the secondary members. So I have allowed them to go for riveting for all those locations, and that otherwise that will affect the production in a very, very adverse manner. So in my opinion, the primary members only should be designed for HSFG, and secondary members, they can be riveted or they can be bolted simply.
So one other question by SIR, I don't know what it means, is lessons learned at this stage of design, construction and maintenance. Would you like to throw some light on it?
There are many which I have learned for the last 20 years. I am still learning, but they cannot be deliberated in a few minutes. You need to have a session for that.
So Arun Kumar Ganasekaran is asking the same question, is how is pre-stressing by force fitting carried out at site? Is any special equipment required for bridge with large cross-section members?
I think for this purpose only, we had a separate lecture on IIB where the complete details, including design, fabrication, inspection, and then that method of force fitting was discussed at length. So this should be available at IIB site, I think. I would request Mr. Arun Kumar to kindly go through the IIB site and find the relevant lecture there. It is very interesting to
looking at so many questions on this topic, let us have one more lecture sometime, which will be only on pre-stressing of steel open web girders.
I think previous lectures have covered almost everything.
Right. Okay, so let's decide. Let us see. Let us think. Then Sahil Hatali is asking, can you explain regarding LWR forces considered and code for the same?
This is a very important topic for which we don't have any Indian code. Whatever we have is a UIC code, and everybody is following that. But I think there is a great scope of doing research on this topic. It will reduce the cost of structures substantially if somebody does a very systematic research on this topic. It's a very important topic.
So questions are over, and thank you very much for this. Now, before we come to a closing session, I'll request Ms. Purnima Singh if she has to say a few words, or she would like to say a few words. And Purnima ji will have to unmute yourself before you speak. Ms. Purnima Singh, would you like to say something? All right. So I think she has chosen not to. May I request? Okay, Goel Saab, would you like to say anything about the whole thing and whatever? I mean, you like to add anything?
I think I have spoken enough.
Okay.
If there is any specific issue, then I can definitely give my remarks.
Okay. So, Deepika, if you are there, can I request you to propose a vote of thanks?
Yes, sir. Thank you, sir. To all the honorable dignitaries, it's my privilege to have been asked to propose a vote of thanks for our special lecture. I, on behalf of IIB, extend a very hearty vote of thanks to all the members and non-members for gracing us with your presence and sharing with us your valuable feedback and suggestions. Firstly, I would like to thank our Director General, Engineer Dijik Dipte, for always providing us with a vision for the future of IIB, our President Engineer Vinay Gupta for constantly guiding, motivating, and inspiring us to achieve the vision. I would like to thank our Treasurer, late Mr. P.R. Kelkar, for being a strong support of IIB. He will always be a part of IIB. Our Honorary Secretary, Engineer Swapnil Joshi, for always managing this platform. Our Honorary Secretary, Dr. Gopal Rai, who's always guiding us throughout in this process. I would like to thanks to our today's speaker, Engineer R.K. Goel, for providing a very informative session on design of open web girders, including pre-stressing. I would like to thank our moderator, Engineer Vinay Gupta, for successfully moderating the session. I would also like to thanks to all our eminent executive committee members for their valuable presence and support. I would like to thank Ruhi Agarwal, coordinator of IIB, for always helping and managing all the events of IIB. Last but not the least, Mr. Josefa for all his IT support. Also to all the huge participants for always coming in huge numbers to make this webinar a success. Thank you, everyone.
So please do join us on 17 June. Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you, everybody. Thank you, Engineer Vinay Gupta ji. Thank you very much for giving me this opportunity to.
My pleasure, sir. My pleasure.
Thank you very much. Hare Krishna.